We're looking at resolution of a force in a given direction, and we'll look at a couple of different approaches to dealing with this, and it's a common thing we need to come to terms with. To be able to do that, we need to basically do the following. We need to understand as our first goal that a force acting on a body has influence in directions other than its line of action, except the direction perpendicular to its line. So what we mean is that when we've got the situation here, we look at, say, pulling something along that's got a fixed path, like on a track or something. So if that's an object that's getting pulled along a track by some force here, given by vector P, it depends what angle it is, but a few things can happen. And if theta increased and the force was perpendicular, there'd be no effect along the line of motion. If it's a fixed line of motion like a track, which was in the direction OX, or along parallel to where vector A is, it wouldn't affect that direction, but it would pull it in another direction. It may not be able to move. It might be fixed if it's on a track. So we're going to have a close look at that in just a second. And part of this video requires you to recall from an earlier unit the vector projection concept, and your formula sheet may have these formulas here. And in this video we're going to use that second part. So the vector projection of vector A onto B is given as such. Now the A and the B in this one perhaps a little bit unfortunately chosen or a bad coincidence, but the A and B here in the formula do not correspond with the A and B on this diagram. What we're going to be looking at is the vector projection of vector P on to vector A. Another way of saying that we're looking at the vector projection of P parallel to A. Okay, so in A's direction, in other words, so P parallel to A. So let's say it's something, let's go back a few steps to go forward. So that's the object there, and it goes along a track OX, and it's fixed to that track. So this object might be pulled along by, like a horse or something, and it's the horse is pulling on that direction there given by vector P. Alright, and let's say the force has a magnitude of P newtons. Okay, so it's given by vector P and it has a magnitude of P newtons. Now, it depends what theta is, doesn't it? So if theta, think about it, if theta is 0 degrees, what's happening? Well, it pulls it directly along the track. The influence does not go away from the track. The entire force is translated in the direction of the track, and we have an acceleration in the direction of the track from O through to X. So the other two scenarios are if theta is larger than 0 but less than 90, and it will also accelerate along the track if it's the only force. But not as much. If P is constant, okay, some of the components or part of the influence of the force will go along through A to X, but some will also go in this direction here, so we can break it down into components. So the influence along OX is less. If theta is 90, so if the force is out here now, basically there are no influence along it, no acceleration along OX, and it will stay in equilibrium in that direction. Won't go left, won't accelerate left, won't accelerate right. And that's assuming it doesn't get pulled off its track or anything like that. So going back to summarize then, so if we have vector P represents force P of capital P newtons, okay, we have A here, vector A is the vector resolute. So A is the vector resolute the vector component. Sometimes the word component's used. The vector component of P in direction OX. That makes B perpendicular resolute. So B is the perpendicular resolute of vector P in that given situation. So along the track OX, A has all the influence and B has no influence on the movement if there's an object free to move along a fixed track, and A is the net effect of the force P applied. Okay, that last point in particular, A is the net effect of the force P applied. So basically that net effect, the magnitude of that net effect A is P cos theta. The magnitude is P cos theta. We can see that by the trigonometry there. Okay, adjacent over hypotenuse. So magnitude of P cos theta is done by a simple right angle trig there. So one way of interpreting this statement here is that the resolved part of a force P newtons in a direction which is created by angle theta has a magnitude of P cos theta, and thus this is the resolved part, and it's called a component of the force in a given direction. Okay, and this statement here looks at the magnitude of that force. Okay, the magnitude of a vector. Let's look at two examples now to finish off the video. And this first one, we're going to use our vector resolute, and the second one is going to use something different. And just remind you, that's our formula there for vector projection, which we're going to use now, especially, as I said, the second part underlined in blue there. Okay, A dot unit vector B of unit vector of B, and that's a scalar, right? And we multiply that by the unit vector B in general. Okay, so if it's one vector on another, so if it's the vector of P on A, we're going to have a P there, A represented there, unit vector, and A unit vector there. So in this given example, we've got two vectors. I'm going to let that second vector 2i minus j, I'm going to call that a different name. Let's call it A. Alright, so find the component of the force vector F 3i plus 2j newtons in the direction of the vector 2i minus j. So we want to find basically the projection of vector F on vector A. Alright, so using our vector projection formula, we've got this. Better put my tildes in. So if you want to break it down, firstly, to get the unit vector of A, we get the vector of A and divide it by its magnitude, which is root 5. You can do a bit of Pythagoras by now, and one way of writing that is this. Now, to find the dot product is a fairly simple matter now that we've got unit vector of A. I'm going to take the 1 over root 5 out the front, and we put the vectors in there, 3i plus 2j dotted with 2i minus j. If you take the dot product and multiply it by 1 on root 5, you get 4 over root 5. You can try that yourself. Okay, from a different angle, oh, that's a pun. There you go, that snuck up on me. We're looking at this force system here, and we have to do two things: find the magnitude of the resultant of these forces, well, that's familiar work, and then B, the direction of the resultant force with respect to the 5 Newton force. Now this one's not using the vector projection formula, it's using a different approach here. So let the 5 Newton force be in the I direction, so let the I direction be for the 5 Newton force, so I's going out that way. All right, that's very convenient in this particular case. Okay, so that's the 5 Newton force then, as a vector, would be 5 I newtons. So the 3 Newton force and the 2 Newton force both need to be determined now, and we use our components. So the 3 Newton force, breaking that down, so that'd be in the I direction 3 cos 30 I plus 3 sine 30 J. For the 2 Newton, we've got 2 cos 45 I plus 2 sine 45 J. The total force, or the resolved force, is the sum of all the corresponding components together. So for the I's, we have 5 plus 3 cos 30 plus 2 cos 45. All right, put them together with the I operator, and we've got, for the J's, we've got nothing for the 5 Newton force. We've got 3 sine 30 plus 2 sine 45, and that's all in the J. And you'll find on this one, instead of trying to muck around with exact values, decimal approximation, I've taken mine to 2 decimal places. So that's our total force. Okay, so that's part A. Now this total force has a magnitude and a direction, and we've got to find the magnitude for part A, and we've got to use the direction in part B. It's because in part A we've got to find the magnitude of that resultant, and part B we've got to find the direction of the resultant force with regard to the 5 Newton force. And this one's easy because it's in the I direction. If it wasn't, you might want to use the vector resolute formula instead. So using our usual way of finding the magnitude, and we get 9.47 newtons. You can try that yourself. So for part B now, it flows on. So part B, to find the angle this resolved vector, or this total vector resultant makes, I should say, total vector, we've got to use inverse tan. You could draw a diagram, but you might remember from your previous vector work that we do find the inverse tan, but feel free to draw a diagram. It's often a good idea if you want to see that yourself, and you'll find that that direction comes out as such. So if that's your I direction there, it'll be coming out at 17.9 degrees. Okay, so we've got this resultant vector of 9.47, that's a funny 9.47 newtons is 17.9 degrees clockwise from the 5 Newton force. Catch you next time.